zeta omega n multiplied by 2, so I can write this. Okay, this is damping. And plus omega n square x equal to f0 divided by m. Then I want to write at f0 cosine omega t. Okay, then we can solve this. Again, the solution of this equation solution, of course, has homogeneous solution plus particular solution. Okay. And we know that this homogeneous solution for this case, okay, that is the response due to initial condition, meaning that I have I can do any interesting experiment using. Mass, spring, and I also have flash pot. I am putting initial condition, displacement initial condition, and then it's like this, right? And then the response would be cosine, because I'm giving displacement. Let it go. Oh, it decay very quickly, right? And then if I give a initial velocity, stop. It does not understand English. Oh, this is really great. Sine, but decay very quickly, right? Okay. Therefore, I can assume that this would decay rapidly depending on zeta. Okay. But this one would have the form like magnitude and the response would have a cosine form and it has big damping. Okay. And it will oscillate with the frequency omega. But as we see in the previous experiment, depending on the zeta, if we don't have a zeta, the response would be just x cosine omega t, right? But because we have a zeta, there is some phase lag because of the zeta. So then I write omega t minus zeta. This is the phase difference. Okay. the solution can be easily found by just plugging this one over here, right? Particularly, a solution can be obtained always by assuming some solution and plug into the carbon equations. And then we found that XP is the form interesting F0, the magnitude, because this vibratory system is linear, the response has to be proportional to F0. Right? Not F0 squared. And there has to be cosine omega t and the phase difference theta. But also there is some magnification factor, like an amplifier. Okay. You have iPod, and iPod has an input, and you have a receiver, and you can control gain, right? And happily your gain is not a function of omega. If it is a function of omega, that means you have an equalizer. Right? The same things happen in vibratory system. This is sort of equalizer or magnification factor. Depending on the way you see the problem, you can either say this is amplifier, or this is equalizer, or this is magnification factor, or maybe later on you can call it this is a transfer function. Describing all the same physical quantity but different names depending on your point of view. Okay? And this has the form omega n square minus omega square and square, because I have a square root over here. Therefore I have this one, right? But this magnification factor has to be controlled by the damping. In this case, there's no damping. Therefore, magnification has factor only controlled by the omega n square minus omega square, meaning that how far I am exciting the system from the natural frequency. But this case, okay? So if zeta in its damping relation is getting bigger and bigger, this magnification factor go down and down. Right? What about the zeta? You can get it by plugging this solution over there, and you can get it, that is arctangent omega n square minus omega square 2 zeta omega n omega. And this expression make you very sleepy, because I can already see there are several students who are sleeping now, because even though there is a vocabulary omega n and zeta, so on, but you cannot communicate with the physical behavior that is embedded in this expression. That's why Jaron is sleeping, and somebody came in very late.